Hello everyone. We continue with our early universe cosmology lunch, and today we're happy to have Gerrit Farren from Cambridge, who is going to tell us about measuring H0 using the equality scale. So Gerrit, please take it away.
Hi, I hope everyone can hear me if I'm sitting here. I don't know which direction I have to speak, but thanks for having me. Thanks for the invitation. I wanted to talk to you about some work that we've been doing on measuring the Hubble rate using the equality scale with present and future galaxy surveys. This is some work that I've been doing with Oliver, with Blake, and with Eric. And most of what I'm going to be talking about has appeared in these two papers here. And then the third one is actually out, I think, as of yesterday or 2 days ago. Sorry, I didn't update the slides there, but so yeah, have a look there. I'm happy to share the archive number for the third one. Anyway, before I dive into this, I just wanted to pluck one of my other projects real quick. So this is just some cross-correlation work between ACT CMB lensing and unwise galaxies. And we have this really high significance cross spectra that we can use to break the galaxy by sigma 8 degeneracy. And it's building on some work that Alex Kulevsky and Simone Ferrara and their collaborators did with Planck and unwise. And so for this we forecast about 2% constraints on S8. And so yeah, if you're interested in that, please talk to me. So it'd be interesting to talk about that as well. Anyway, for this project, I mean, we'll all be aware of this like long-standing tension between the H0 that's been measured from the CMB with Planck here and what the local distance ladder measurements get you, for example, from shoes. And with the most recent data, that tension is up to about 5 sigma. But Planck is not the only CMB measurement that we have H0. We also have this measurement here from ACT plus WMAP, which is in perfect agreement with Planck, and some other indirect probes that we have. Indirect meaning that they require a full cosmological model to interpret their data are, for example, Galaxy BAO and also Galaxy full shape power spectra. And all of those indirect probes come in agreement with Planck around H0 of 67. While on the side of the direct measurements, things are a bit more uncertain, I would say. It's not quite as clear. But this tension with shoes has sort of been long-standing, and it's sort of survived multiple iterations and refinements, and people have investigated systematic effects, but it's still there. And so, yeah, clearly could still be due to systematic effects. And if you ask me personally, that's probably the most likely. But it's sort of difficult to identify where those systematics are, because on the indirect side, there's different data sets involved. So it's difficult to point to where exactly that would be. And then on the direct side, people have really done a lot of investigation into this systematics, and so far nothing has cropped up that explains this. So maybe there's something else. And something that all the indirect probes have in common is that they rely in some form on measuring the apparent size of the sound horizon at decoupling, and then comparing that to some model predictions. The way that the sound horizon enters this is that it imprints a characteristic scale in both the CMB as well as the large scale structure. So that comes from the distance that a sound wave could have propagated prior to photon baryon decoupling. And so to sort of illustrate that here, and sort of as a reminder, essentially, if we start with a density perturbation in the primordial plasma, then because the photons and baryons are tightly coupled, the photon pressure drives a sound wave that propagates outwards from this perturbation, while the dark matter sort of lags behind, since it's only affected by the baryon's gravity. And then at photon baryon decoupling, this wave stalls. And because the pressure support is gone, and that imprints the sound horizon scale primarily first in the CMB. And so there's this characteristic scale on the CMB that we can measure and use to measure H0. And then over time, because the dark matter and the baryons interact gravitationally, their distributions assimilate, and you get that same characteristic scale that is also present in the large scale structure. The way that we would then use that to measure H0 is we measure the angle that is subtended by the feature that's associated with the sound horizon. In parallel, we compute what we think the sound horizon is in our model, and then we can use that information to infer the distance. And because that, again, depends on H0, that gives you inference on H0. Clearly, this picture is slightly more complicated if you also have redshift information, but in principle, this is similar. As you'll probably know, this is not what we do in practice, but this information on RS is encoded in the spacing of the acoustic peaks of the CMB, and then the spacing of the BAO wiggles in the matter power spectrum. I should probably caution that, yes, these are slightly different, right? What's relevant for the BAO is the sound horizon at decoupling, and what's relevant for the CMB is at recombination. But for the sake of simplicity, we sort of neglect this, and it's sort of been argued that there wouldn't be much scope for physics that affects those two things largely independently. Okay, so if we take this Hubble tension that we've seen as an indication that lambda CDM is wrong, so we just accept it at face value, then we have essentially two choices. We can either change the comoving size of the sound horizon, for example, by changing the pre-recombination expansion history. Alternatively, could also change just the sound speed in the early universe, or we can change the way that the distance depends on H0. The latter is sort of like a late time resolution, and that has been argued to run into lots of problems with, for example, the inverse distance ladder measurements. So most people have focused on those early time resolutions by making pre-recombination modifications that change the size of RS. Some that have been proposed include, for example, early dark energy, where you have a dark energy-like component in the early universe that drives a period of accelerated expansion and thereby changes the comoving size of the sound horizon. Alternatively, you could have like strongly self-interacting neutrinos, but there's many, many more models. And if you want to test them all, you have to essentially test them individually or rule them in or out. And so we want some way of doing this somewhat model independently to not have to look at these literally hundreds of models independently for every probe that we might have available. And one way to do that is if we can find a probe that is independent of the sound horizon. And in fact, there is a second scale present in the matter power spectrum. That's the scale of the horizon at matter radiation equality. And that's related to the turnover scale of the power spectrum because it corresponds to the transition between modes that enter the horizon in the radiation-dominated and in the matter-dominated epoch. But we don't have to resolve this exactly because there's also information on the larger K modes about what K equality is. For example, through the fact that the power spectrum scales logarithmically with K equality. Also, this transition between the peak and this logarithmic scaling tells you something about what K equality is. And if you have a prior on the primordial amplitude, then you can also use the amplitude of this in this area to constrain where the turnover happens. And we can use this information in a very similar way to RS to measure what H0 is. So again, we would measure the angle that's subtended by this feature, and that relates to H over K equality. And in lambda CDM, that's approximately omega matter times H, all of that inverse. And so if you have information on omega matter, then that allows you to measure what H naught is. Right. Yeah, any questions so far at this point? All right. If they're not, then I would sort of like to convince you that these are actually physically independent probes of H naught. So we can get some insight by separating out the equality and the RS-based information. That's because the sound horizon and the equality scale are sensitive to modifications of the pre-recombination H of Z at different times. You see that here on the left. So essentially what we've plotted is a change in the contribution a change in H of Z would make to the equality and the sound horizon scale. And this range of Z of a couple of thousand, they're very different. And that's exactly the period where early dark energy, for example, would be active. And so we would expect that such a modification or a similar one should show up as an inconsistency between our equality and RS-based measurements. And it seems sort of unlikely that any new physics you could come up would conspire in just such a way to affect both of those the same, so that you would still maintain consistent results if you were in fact assuming the wrong cosmological model. And then so Eric and Blake showed that this can be done using CMB lensing. They measured H naught using K equality from CMB lensing with Planck. That's because CMB lensing is sensitive to this product of the equality scale and the distance to large scattering, which approximately goes as omega matter to 0.6 times H. So again, you get this this information here out there, and this probe is independent of RS because the wiggles in the matter power spectrum are washed out by the projection through the lensing kernel. And so what they found was H naught of 73.5 plus or minus 5 and a bit kilometers per second. But they also showed in forecasts that you wouldn't be able to necessarily improve much on this. And that's what we sort of wondered, is there a way that we can do better? And so we looked at galaxy surveys. So here we now need to explicitly avoid the sound horizon information because in contrast to the CMB lensing, the BOO wiggles are clearly a source of information on the galaxy power spectrum. And if you don't do anything, then that will just dominate your constraints and you won't be able to do the measurement that we're looking for. But what we can do instead is we can leave the sound horizon explicitly uncalibrated. In order to compute the sound horizon, you need precise knowledge of what omega baryon is. And so if you don't give that, you don't have a calibration of the sound horizon, and then you can't use it to measure H naught. And that's sort of the reason why there's this strong degeneracy between omega B and H naught. And so we chose to not provide that information and instead try to use the equality scale information by providing this prior on omega matter, as I have discussed. You can get that, for example, from uncalibrated supernovae, which is what's shown here from the Pantheon sample, or you can also use uncalibrated BOO. And here we used the EFT model that Misha and collaborators have developed and to find with BOSS data and this Pantheon prior on omega matter, but 65 and a bit plus or minus a few kilometers per second. This was work that was led by Oliver, but this is not a bad measurement, but it's not super competitive with other results, and that's because this is sort of a suboptimal analysis. We've actually erased more information than we really needed to. For example, the amplitude of the BOO feature gives you information about the ratio of matter to baryons. And so this information is now also gone because we haven't included a prior on omega B, and so that also degrades our constraint on omega CDM. And so here, this information has been removed, and we would like some way of retaining it while still getting rid of the information that we explicitly don't want, which is the sound horizon. And so ideally, we'd like to do that directly, but we can't because the sound horizon is not an input parameter to our theory. So what we do instead is to marginalize over the source of information about the sound horizon. I told you this is included in the scaling of the BAO feature. And so what we do is we explicitly rescale that BAO feature. We did add an additional parameter that rescales it. And so that is now perfectly degenerate with the sound horizon. And so you've removed that information content from your analysis. In practice, we split the power spectrum into broadband and the wiggly component based on some technique from the EFT of LSS, where the BAO peak is removed in the real space correlation function. You then transform back to the power spectrum and get the BAO only power spectrum as the difference between the original and now BAO free power spectrum. And that's already necessary to do IR resummation to accurately model that BAO feature in the nonlinear power spectra. And you see here on the left what that sort of looks like. As it's sort of what you expect. The wiggles are being shifted through that rescaling parameter. And yeah, there's obviously a rather extreme change here that probably would be highly constrained by our model, but anyway. Yeah, and so I should mention that there is in principle a second source of RS information in the power spectrum. That's the scale below which baryon drag suppresses structure formation. But we did some tests on that, marginalizing over that as well, and found that it is essentially a negligible source of information for this kind of analysis. So we neglect that for the remainder. Now, we then ran a series of tests to confirm that our results were in fact independent of the sound horizon. We compared to a BAO-only analysis, where we marginalized over the broadband using a theoretical error prescription. And then we found that if we included RS marginalization, that degraded our constraints dramatically. And there was essentially no constraint left. And so that this was sort of indication that you can't get any sound horizon information if you have that marginalization procedure. Additionally, we also compared to this forecast, which is done with an Eisenstein-Hu model. Within that model, we can do this marginalization exactly, and we find excellent agreement. So essentially all the contours line up pretty much exactly between our run on the mock data with a full MCMC that has our heuristic marginalization procedure and the exact marginalization procedure from the Eisenstein-Hu model. Lastly, we also looked at this parameter combination, which is approximately proportional to the sound horizon. And we found that the degeneracy between this and H0 is significantly reduced when we include our marginalization over the sound horizon. And so all of this gives us confidence that this method is actually doing what we thought it was and what we intended it to do. And so we then moved on from there to do analysis on some actual data and then also some forecasts. But before I get to that, I was wondering whether there was any questions on this so far. All right, then we'll move on to applying this to the BOSS data. So these are our most recent results on BOSS data with a prior on omega matter from uncalibrated supernovae. This time, this comes from the Pantheon Plus sample, so it's an update on what I showed you previously from the Pantheon sample. We also include a prior on omega baryon from Big Bang nucleosynthesis. And we find H0 that is in statistical agreement with the CMB, but in some tension with shoes. And then additionally, we can add CMB lensing information to further tighten this constraint. In this case, the central value also is dragged down a little bit. And what we get is H0 of 65 plus or minus 2 and a bit kilometers per second. I should note that in comparison to the earlier lensing results, the Pantheon Plus omega matter is about 13% higher, and so that leads to the Planck lensing inference being somewhat lower than what Blake and Eric previously found, and that's why this falls somewhat lower than the galaxies alone. Now, this is obviously a relatively competitive measurement already at this point, but we also looked at some mock data for a futuristic, well, not that futuristic, but Euclid spectroscopic survey, and we forecast that we could achieve an error above 0.7 kilometers per second, which is relatively competitive with the BAO only as a result, which is about 0.5 kilometers per second. And interestingly, these numbers line up exactly if you just add them together, add the errors together, you get exactly what you have when you do a standard full shape analysis that gets this information from sound horizon and equality. And so this is possibly some further indication that sound horizon and equality scale give, in fact, physically independent measurements of H0, which, if you combine them, then you would expect exactly this sort of error. Now, something that maybe one would be worried about, and maybe I'm trying to convince you that you shouldn't be too worried about it, is possible systematics. There might be some concern that in the galaxy power spectrum on large scales, there could be the impact of some systematics, particularly with future surveys, where the error bars will be obviously a lot tighter than the current data. And that is mostly due to sample incompleteness that could be spatially correlated with things like stellar density or galactic extinction, or also atmospheric disturbances, even though that's obviously not an issue for Euclid. And so this was seen, for example, in the SDSS data. And they saw that there was this correlation with the stellar density, and if they didn't correct it, they had these rather large biases on large scales. And then on these intermediately large scales, they were able to correct for that mostly and remove that bias. But on really large scales, there might be some bias still remaining. Essentially, what all of those effects have in common is that they give you additional large scale correlations, which I've sort of shown exaggerated way here on the left. But because there's quality information also on larger K, things are maybe not as bad as you might think. So we've previously found, for example, that when we increased our K-min from 0.01 to 0.03, that degraded our constraints by about 15%. So yeah, so we are optimistic that these systematics can be controlled, but there's clearly some work here to be done to demonstrate that in practice. But also there's also new methods being developed for mitigating those. So I think with future surveys, we should be optimistic that that can be done. All right, and if you can do that, then we get this sort of cosmological consistency test between lambda CDM and other models. So what we did here, we looked at early dark energy as an example model. On the left, what you can see is mock data that's generated with lambda CDM, and you see all our analysis choices give consistent results. We have the full shape analysis plus marginalization, and then we also have a BAO only analysis, and they all give consistent H0. And then in contrast, on the right-hand side, we have mock data that's generated with an early dark energy model, but then analyzed in exactly the same way as the lambda CDM data. And what you find is that there could be potentially large tensions between the equality and RS-based measurements. This particular model that is shown here is fit to the ACT data. This is results from Hill et al. In 2021. And for this particular model, we forecast 9 sigma tension between the BAO and the full shape plus marginalization. This is a rather extreme model, and the paper does acknowledge that there might be some issues with systematics that are currently under investigation. But even when we look at data, an EDE model that's fit to Planck with an additional prior on H0 from shoes, we forecast about 2.6 sigma shift between the equality and RS-based measurements. All right, just to summarize, we've argued that we can use the equality scale to measure H0 in a way that's distinct from the CMB and other LSS probes. We developed this method for marginalizing out this information from the galaxy's power spectrum. And we found these relatively competitive constraints with BOSS. We think we can do really, really well with future Euclid data. And then this can be used as a generic probe for RS modifying extensions for lambda CDM. And I'll just leave you with this figure, which now has our RS independent, large scale structure constraint. Yeah. All right. Thank you. And I'm happy to take it.
Questions? Okay, maybe I can ask one question. So this K quality measurement is so it's relatively stable with respect to cosmological model, the underlying cosmological model that you assume, right? Because you said that for lambda CDM and this ACT early dark energy, you get essentially the same K quality measurement.
H0, like inferred H0.
Right, right.
Yeah, it's mostly stable. There's sort of a small, actually, the K quality inferred H0 in the EDE model is sort of lower than the lambda CDM fiducial value. Mm-hmm. But yeah, I think it's consistent with it, and particularly for the Planck quantities, you wouldn't see it.
And the quality scale also K quality. If you were to extract K quality in megaparsecs, it would also
yeah. So this is actually a bit complicated because in EDE that's not something you can like very straightforwardly define, right? There's an additional relevant component around that time. Right. If you compute it naively, the size of the horizon at matter radiation equality, that actually changes quite a bit. Mm-hmm. However, when we do this, when we do this analysis, we essentially get a best fit lambda CDM model, and if we compute K equality within that model, then that agrees quite well with the standard lambda CDM value.
I see, but it's more like sort of a coincidence, right? Because
yeah, I'm not sure it's coincidence. I think it's related to that you in fitting to the CMB might already have some information mm-hmm. on what the equality scale is, and so you need to match that turnover still. Right. And so I don't think it's coincidental. But yeah, defining what K equality is actually sort of not straightforward in EDE. So
right, yeah, I see.
Yeah, what you'd want to compare is probably the turnover scale of the power spectrum. Yeah.
Right, and the second question I had about the K quality measurement from the CMB spectrum. Do you think that it's possible?
Yeah, I think this sort of what we just talked about indicates that there is probably some equality information in the CMB spectrum. We haven't exactly quantified how well that can be measured from that. But yeah, it seems like there's probably some information, which is the reason that when you do this sort of fitting of this lambda CDM model to the EDE data, mm-hmm. you recover a K equality that is very similar to the fiducial lambda CDM model.
Okay, good. Any more questions from Zoom? Okay, if not, then let's thank Gerrit again. We're moving to our second speaker, Kaze Wong from the CCA. So Kaze, do you want to share your screen? Yeah, good.
All
right.
Can people hear me right? Do I need to speak loud, or is this okay? I don't know whether I can.
Yeah, that's fine.
All right, that's fine. Okay, good. So hi everyone. I'm Kaze. I'm from CCA. I do mostly gravitational wave and not really cosmology. But at some point, I think Christian rolled up to me and said, "Hey, Kaze, you want to give a talk at Princeton or IAS?" And it's like, "Yeah, sure, why not?" And then I didn't realize it's a cosmology thing at the time, but like later on, I was like, "Okay, cool." But yeah, I'm gonna still talk about gravitational wave, but I have some more introductory thing. So let me know if you have any question in a way. So today I'm gonna talk about like something that also when I was told to do this, I was like, they're trying to ask me to do something unorthodox. It's like, good, that's what I'm about. This is kind of a weird idea in the community that we're about to publish a little bit. And I'm sure like within the community, people will flip a lot. So that's good. Let's see whether the people in cosmology flip on this idea as well. So let's go. So before we jump into what exactly we're doing, let me just introduce to you what LIGO is still hyped about. It's like the first event that we have detected, it's now what, 7 years ago almost. So this thing is getting old. Why are you still hyped about it? Why should we still study gravitational wave? And what really we should learn about. So this is the first event. You can see like different phases of the first gravitational wave discovery. And since then, we actually have quite a lot of events coming in, like big and small, different kinds of them. And this screen cap, I took it, I think, a year or two ago. But and LIGO haven't made any new detection since then, so this still stands. But in the latest observational run in LIGO Virgo collaboration, they have around 56 events. So we have a lot of events, all right? So since then, they have published quite a lot of papers and received quite a lot of citation. And this is what I got last night on their paper webpage. And there's this mythical GWTC3 thing. So what are that? That actually stand for Gravitational Wave Transient Catalog 3. So they actually have already put out 3 catalogs about gravitational wave. And in those papers, what people are looking into these days in gravitational wave, mostly in terms of science, is the population behavior. Like what are these sets of catalog of gravitational wave can tell us about the universe, what physics we can extract from them. So on the leftmost panel here, you see the population posterior. So what we think about the population distribution is in the primary mass on the x-axis and mass ratio in the y-axis. So this is the black line is what we think in previous catalog, and the blue are new addition of gravitational wave events. So each contour is basically one event. And so you can see they exhibit some pattern. There seems to be a cluster of things here, and there are these weirdo living here. And there are different plots that people made. On the middle plot, this is the effective spin. So basically how spinning is the binary system against chirp mass, some other mass. And on the right, you have redshift versus primary mass. So I mean, we don't need to look into too much of the detail of these plots, but the point here is these patterns on this different distribution of observables from these catalog of gravitational wave should tell us something about the universe. Either it's cosmology, probably some things about the cosmology or star formation on the far right, or formation channel, like the spin could be some indicator to where are these black holes, what is the environment that these black holes come from. So that's kind of what we are going after in the gravitational wave communities, to study a population of gravitational wave and trying to get physics out of them. So to really drive the idea home is like, I know people just talk about supernova earlier today, but I'm going to use it as an example of like, illustrating what gravitational wave population is about. So at some point you can measure the light spectrum of a system, and you can look at the spectrum, which is on the left. I put it on Google, and study the properties of a single source. That's kind of what we do. What we did when we first have gravitational wave. We have a waveform comes in and try to understand what is the mass and the distance to this particular event. And later on, we have more and more of these events, so like they start to form a line, and there's some pattern or some relations between different dots. And you can draw a line, and you can extract some physics out of it, whether it's cosmology or some other physics. So that's kind of what, at least my understanding of what supernova cosmology is about. So let's see what the picture looks like in gravitational wave. Again, 7 years ago, we look at the waveform and say, these are black holes. They are 30 solar mass, they are redshift 0.1 and something like that. Today, we have a lot of events. We have a population of them. There's some pattern. Now the question is, what's the physics? So that will be the theme of the talk. Okay, is there any question at this point, just to be clear? No, good. All right. So how do we really study a population of gravitational wave? I mean, I give you the observable, I give you the data. So how do people do it? How do people extract physics out of it? This is not the only way, but this is one way that people do it, is through population synthesis simulation. So what is this? I mean, like this word should look gibberish to me, but to you, because like not everyone in the world do synthesize a population of binary. So what exactly is population synthesis simulation? So the premise goes like this. So you first write down an initial condition for your star population. For example, you have your initial mass function, you have some star formation history. So then you write that down or pull it from like some model, you draw samples from that. So for example, you have a star formation history that is coming from the Medal-Dickinson star formation curve. You draw samples of binaries, or according to that, like trying to draw a bunch of initial binaries, say stellar binaries from them. So you have a member list of a catalog of stars, all right, or progenitors. Then you have some evolution process that is like this is a very schematic view of what we're doing, but essentially this these evolution process, which is the simulation itself, takes in whatever properties. So F is the process that evolve your binary, okay? Theta prime is the progenitor properties. For example, the mass of the progenitor star, or the initial separation, things that is related to this particular binary. And lambda is something that we usually call hyperparameters, like some physical parameters, such as how strong is stellar wind, or what is the typical natal kick this system receive. So it's some extra parameters that you put in your simulation. In the cosmology context, it could be, I don't know, omega m or something, whereas theta could be the mass of that galaxy. All right. So you take these lists of events, plug them through this evolution process, which is your simulator, and then you have a catalog of these compact binaries. You can believe with white dwarf, neutron stars, a single neutron star that won't produce gravitational wave, which is what most of the stars do. They just end as a single white dwarf. They merge before they become a compact object and don't emit gravitational wave at all. And those do nothing. Some of the heavier event, like heavier stellar binary, they may form binary neutron stars, and those will be detected in both EM and gravitational wave at some point, back in the day. And of course, some of them will form black hole binaries, and again observed by LIGO. So then you can take this synthetic, you can collect all the product that you get out of this simulation and compare that to the data. On the right is actually more of the black holes that we have seen and neutron star compact objects that we have seen, both in LIGO and EM observation. So you can take your synthetic catalog, compare it to data, and say how much your synthetic catalog or how much this evolution process agrees with the observation. So that's kind of what people do. So again, just let me briefly recap. You write down your initial condition, you take your code for modeled samples drawn from this initial condition, collect all of them into synthetic catalog, then you compare with data and you say, okay, this one's bad. Let's change the hyperparameters. So that's what people have been doing before I comes in. So on the left, this is like a horrendous. Like the reason why I put this plot here is like to make you not look at it, because when you look at it, you should have some physical reactions like this is bullshit. But basically here you have gravitational wave measure rate. Like you don't even need to read the word. I intentionally make it not readable. But all these different models is different population synthesis simulation to trying to compare the rates of detection to LIGO. So LIGO detect 56 event in the third observation. So what they're trying to predict is, do we have 56 event in like a year time span, given all the detector and model and stuff like that. And some of them do, some of them don't. Most of them are consistent and stuff like that. So using rate is one, the detection rate is one of the handle that you can have to compare with the observation. Another comparison that you can do is like after you collect your catalog, you can look at their mass spectrum, right? Like you can look at the mass distribution and try to compare them. So this is a study by this, he's kind of a famous guy in the field. But basically he does all these population synthesis simulation. And after he collects his catalog, you can bin them basically and form, like for different models, he has different prediction for the mass distribution. So shown in different color curve. Okay, so on the x-axis is a primary mass of these of the binary system, right? And so the dashed curve is kind of the bound they had from LIGO. What this guy did for many years is just produce this catalog, overlay them with LIGO prediction, and say, that looks about right. It's not a statistical statement. It's just like, okay, it's more or less on the same level. Good. That's kind of what people do. That's 2020 and 2021. Last year, depending on which month you're looking into, but last year you can, I was been working on this in my PhD. I've been working on simulation-based inference. So you take these population synthesis simulation that make a predictions on rate, make a prediction on mass distribution. You can plug it in these things that I think in cosmology they kind of do that as well, like simulation-based inference pipeline, whatever algorithm that is. But the idea being, you pick a hyperparameters that you want to simulate your simulation, you plug it into your simulator that will generate a catalog, then you make that catalog and take the data, write down a likelihood that compare your catalog and the likelihood, then make a proposal. So there's the input part, you take the hyperparameter, move it into simulation, you generate the simulation with whatever code that you use, and then you do accept and rejection. You can plug it into an MCMC using your likelihood and try to get samples of that. And what I'm trying to lead to is this figure that like in the paper that I wrote last year. So alpha, RV, F, they are different hyperparameters that has to do with the process that we've seen before. So like when we say we have a simulator that forward model this population of a black hole, they can be parameterized by some hyperparameter, and these are those hyperparameters. So alpha is something known to be a common envelope efficiency. So how efficient the binary is in to eject the envelope that engulf them when they're about to merge. So they will blow the envelope away. So there's some prescription of how efficient that process can be. RV is if a binary is come from a cluster, how big the cluster, basically the radial velocity of the dispersion, velocity dispersion of the cluster. So kind of like the size. And F is the mixing fraction of field versus cluster formation. So if F is 0, I think it's coming from cluster. If F is equal to 1, it's coming from field. So you can plug whatever simulator that people use into these simulation-based inference pipeline that we have and get a posterior on the population with quotation, population properties, which is, for example, what I've shown on the right. And at this point, you should be confused by a lot of things because it's a very brief and whirlwind description of what we're trying to do, but that's intended. Because actually, after I write this paper, I spent some time in my PhD doing this simulation-based inference things and trying to extract physics out of this simulation. But like earlier this year or late last year, I figured out this is bullshit. So I'm here to confess. I don't want you to look at this as like, this is the way to go. I want you to look at this and it's like, okay, this makes no sense. And first, this is not scalable. The reason why, like, there's these 3 hyperparameters here, which, we generate a bank of simulation, train a machine to do it, and, form the likelihood. But the higher dimension of yours, the higher dimension of your parameter space is the more training simulation that you need to train to form the simulator that you can plug it into an inference pipeline. So here we have 3 hyperparameters, but imagine, these code that generate population, they may have like 20 parameters, and they're not standard. In cosmology, you have 6 parameters, that's it. In this population, well, you can argue that, but in this population simulator, they could have easily 20 parameters because people haven't figured out how to standardize the model. So a non-scalable machine is not favorable because you just can't attack the problem in whole. Second, I actually kind of trap you guys into thinking that was the right picture that was intended again, because we actually made a very strong assumption on the population when we do that whole simulation-based inference or population synthesis model is why we are assuming there's a population parameters about the whole population. Like, for example, when I say common envelope efficiency or velocity dispersion of the cluster it comes from, there's no reason why you should assume all the binary black hole coming like that we observe comes from the same cluster. There's no reason why they have to come from the same environment. They can actually come from different environments. So when we do the population synthesis, we actually commonly assume they come from a fixed set, a Dirac delta distribution of hyperparameters. So that actually makes no sense. Different event can come from different environment. And in this paradigm, it actually doesn't allow that. And of course, like the most important part here is after you form the population and only compare your statistic on the population level, you actually ignore all the information that individual event has. So that's kind of bad. And today, main dish is really about talking about this new thing that instead of looking at the problem on a population level all the way through this population synthesis simulation, let's think a little bit more and think about how can we attack this problem a little bit nicer. And now here we go. We are like any super confusing thing. I mean, you should be confused, but that's intended. Now it's time to, in the following 10 minutes, I'm trying to clear things up a little bit to see how things should be done. Well, at least that's what you think. Any question at this point? Good. Cool. So GW150914 is the first event, just to give you the phone number. And let me just pose a question and try to look how to solve this particular problem first. So if I give you the posterior of GW150914, the first event, in the two observed mass, okay? So what you see on the right is what LIGO thinks the masses of the first event could be. So this is its posterior. Now I ask you a question. What is the possible configuration of its progenitor to generate this thing? And how does that translate? So really what I'm asking is like, okay, if I have a simulator, what is the possible state in both progenitor properties? So what is the possible progenitor mass? And what is the possible environmental, these hyperparameters? For example, what is the velocity dispersion? If this is coming from cluster, what is the velocity dispersion of the cluster it comes from? Okay, so all we're asking is like, if I give you this event posterior and I give you a simulator, now go find all the possible, let's say, for simplicity, let's just say the initial mass or the Zam's mass of the two star. Okay, so this is the problem that we're trying to solve. How can we solve it? I mean, I can go into detail, but like, you know, let's not worry. This is the task. Okay, I give you a posterior, give you a simulator. Now let's go figure that out. So if you, I'm not going to go into like the detail map. How do we do that? But like, if you do this, what will you have? The answer is something like this. So on the left, this is a horrendous corner plot again, but bear with me for a moment what this is. So here is the first event when it was a baby, when it, like the progenitor properties of GW150914, the first event. So these corner plot up here is the progenitor mass of the two. We have some assumption. I can talk about the assumption a little bit later. It's a particular simulation that we use. But using the simulation, you can actually ask what is the possible progenitor mass, and this is what the simulation will tell you. Oh, it has to be a certain mass. It cannot be too light, but it also cannot be too heavy. Actually, we found that there's an interesting branch of possibility here, which we're still exploring what's going on. But these are the theta. These are the progenitor properties. I think these two are the mass. This one is the metallicity that associated with this binary. This is the redshift distribution of possible progenitor redshift. So where is this progenitor first form? And the rest are lambda, are hyperparameters. So like what is the common envelope efficiency, stellar wind, and whether the accretion during stable mass transfer is conservative or not. So that's what you can do. You can backtrack all these out. And if you take this posterior and reproject it, you plug it into your simulator again, you can find it, of course, as expected, agree with the first event. So the orange and the green line is what the LIGO posterior looks like. That's the data. And the blue line is like you take this progenitor posterior and put them back again to try to compare with the data, like to make sure that you're doing the right thing, because it's not necessarily true, because the simulator can have a problem sometimes. So this is a sanity check to make sure it agrees with the observation. So you can do that. But what's more interesting about now this method is, okay, that's the first problem. If I hand you a gravitational wave event, all right, I give you a simulator, you can backtrack its progenitor state. So what? Like, okay, then the interesting thing is once you do this, you're actually not subject to some of the limitation we had before. I'll show you in the picture. So previously, this is our picture, right? So this is how people used to generate catalog and compare with the data, right? You take the initial condition, forward model by assuming some hyperparameters that you care, make a catalog, compare with data, good. Now, once you're able to bring an observation back to the initial state, this is what you can do. So instead of doing this, what we do, you can do that. You can start from the data. So let's say, well, I mean, this is not the perfect illustration, but because this is a single neutron star, but bear with me. So what you can do is, given every binary observation, you go ask for the initial progenitor, like posterior in the progenitor space, right? You take this function, you do the exercise that we just did, find the progenitor properties, right? So like for maybe for the first event, you get one posterior in the progenitor space. You repeat this for every single event in the catalog, okay? And the critical observation here is you don't have to assume a common lambda for all of the events. And what this means is once you take all the data, like, you know, all the event, bring them back into the progenitor state, then you can fit whatever population model on this side instead of doing it on the data side, which means you can do the following thing. So what is this magical plot? So on the x-axis is index of events. So like originally we're going to plot it on mass because but like the problem of plotting them on like a linear mass scale is some event is going to clutter together and you can't see things right. So we just index them and sort them by mass. So on the low end side, you have binary neutron star basically. On the high end, you have the heaviest event, heaviest binary black hole merger observed by LIGO. On the y-axis, it's one of the hyperparameters that people care. And it basically tells you if a binary gone through some stable mass transfer, whether the mass transfer is conservative or not. If it is 0, it's totally not conservative. All the energy and mass get like, you know, ejected to ISM. And if it is 1, it's fully conservative. So like the donor will give all the mass to the other companion. So as you can see here, and each bar is basically the posterior for that event. So blue mean is more likely for this event to come from a non-conservative stable mass transfer, and if it is 1, it's a conservative mass transfer. So what this is telling you is for binary neutron star, we actually favor non-conservative stable mass transfer, okay? And for if you go higher and higher in mass, the mass transfer become more and more conservative. And this is kind of our newest result that what we show. But to contrast this with what people will previously do, what people will do previously is you draw from an initial population, you pick one FX, you pick one number, and you simulate that for the entire population. And you forward and you compare with LIGO and you say, okay, maybe 0.6 doesn't work for the whole population. Then you ask like 0.5, does that work? 0.4, does that work? But obviously from here, you can see that none of that will work as long as you assume a single FX for the single whole population. So instead of going forward in terms of producing the catalog and compare with data, you can actually start from the data and go back into the progenitor space, then understand your population there, which is what you were showing here. And that allows you to approach the problem much more scalably. You don't need to make these assumptions of like, you know, the whole population come from the same environment. Yeah, so I don't even have a recap screen, but like the idea of this talk is really, if anyone, like, so if you want to take away one thing from this talk, like next time, if there's another gravitational wave people comes in, it's like, let's do population synthesis, you know, let's generate simulation. It's like, hold on, let's, instead of going forward, let's think about this backward direction. All right, I'm just gonna take a question. Probably pretty confusing.
In case.
Do we have any questions? Maybe I can ask a question while we continue. So you started with this plot, for from the data Q as a function of like the other mass. So somehow this Q seems to be order 1 for most of like events. So why there are no, extreme mass ratio binaries or like small Qs?
Wait, so where's the plot? Let me go back. You mean this one, right?
Right. Yeah.
Yeah. So like the mass ratio definition of LIGO is always M2 over M1, where M2 is the secondary, so it's always smaller than 1. So the closer you to 0, the more extreme you go. And the reason why we don't detect things there is mostly because of detector capability. Because like the higher the mass ratio, you either has to be close or it has to be heavy. So the horizon goes down as you decrease the mass ratio. Also, we don't have good enough waveform model for a super extreme mass ratio. For example, 1 in 100, which will be 0.01 here, and this is also a linear scale. So yeah, we haven't detected things. So there's a couple reasons, but the main reason I would argue is the detectability. The secondary reason is probably just like we don't have good enough waveform. And things are not loud enough to be picked up by a model search. So we heavily reliant on model search. So you really need to know the waveform model so that you can detect things. If you don't know the waveform model, you cannot detect it. Right. And we don't have model in those regions.
So you're saying that actually, like I should interpret all these things as also like they contain some sort of selection bias, right? So you cannot detect this extreme mass ratio binaries just because like they don't have produce enough signal in the LIGO frequency band.
Yeah. So there's a huge selection bias toward mass ratio, extreme mass ratio.
I see. What's the is there a value of the cutoff that
if anyone comes out and say we have excellent models of like 0.1, then should squeeze your eyes and say okay, maybe, but 0.1 is about where
I see. So roughly 0.1.
Yeah.
All right.
Can you say a bit about like how many simulations you would need to train this as compared to using like Gaussian processes?
So this one we don't actually train. We just use simulation. So when we do this simulation on a population sense, you counting simulation by population, right? Because you need to draw a whole population and evolve a whole population. So that counts as one population. But the code that people use to evolve a binary is actually per binary. You should count each simulation really per binary, not on a population level. So previously, when we do the simulation-based inference, I think we have like a couple hundred simulation. Each simulation use around 20 minutes or something, so you can parallelize it and stuff like that. But still, it takes a couple hundred, and that's not entirely negligible. You can't run it on your laptop. But once you start to do this, the going back. So in a population, if you want things to converge, you usually have 10 to the 6 or 10 to the 9 members, because not everything forms a black hole, and you want to have enough statistic in the catalog. So you need to have really a large population of stars. So one catalog could have 10 to the 9 test binary to form a catalog. But now, once you liberate that assumption, if you just want to backpropagate one of these events, that can converge in 10 to the 7. So at the end, in terms of convergence, we basically earn around 2 orders of magnitude, because previously we need to run 400 catalog. Each of them have 10 to the 9 members or something. Now we just need to run, like per event, we need to run 10 to the 7 evaluation of this particular function. But then we have 79 events, so you run it by 79 times. So it's around 10 to the 9 if you round things up. But then we just really need to run it once instead of 400 times. Does that answer your question? Jay?
Yes, thanks. Yeah, thanks.
Cool.
All right, good. Any more questions?
Yeah, one question I have.
Yeah.
So this all depends on having a good forward model between the initial conditions and the data.
Right.
Is there any consensus that at the moment we should trust that forward model?
So data, I think, is what I like. The point, like if I want to pitch to Gravitational with people, I would tell them, data is what we can trust the most, because like, okay, LIGO people, we're gonna people don't have consensus on the evolution process. But I think that's the point, because all this year people just don't think about how to constrain them. So people just hallucinate and start to paint their own model and fight since like they don't care each other. And I think the further you go to the left, the less uncertain things it. So it really doesn't make sense to by believing in your initial distribution and believing in your process and trying to shoot to the data. Instead, you should flip the problem around. You start from something that you trust, which is the data, and trying to constrain the evolution process. And so for example, the one of the biggest uncertainty in terms of rates comes from the star formation rate model that you put in, and that has no consensus whatsoever. And people always pick their favorite model, put it in, go get all sort of different answer out, so they can never agree with each other. So by flipping the problems around, you can actually start to find, okay, whether that is constrained or not. Okay, then you filter out the problem bit by bit.
So we should infer the theory from the data.
Yes, instead of
You showed like with the mass conservation ratio. So, you showed that wasn't like there was a terrible assumption to say that they are all coming from the same sort of high parameters.
Right.
Do you have any sense for the other high parameters that you showed, like whether maybe some of them might actually be?
I don't have the plot here, but for common envelope. So this is, I think once we publish this paper, which is hopefully going to happen this month, it's going to be like some interesting discussion, because for many years, people know like common envelope efficiency. It's like a mythical thing that people invent to explain something, and they fail. But people know common envelope is just a proxy. So what that means is it's not fundamental physics. It's subject to a lot of things downstream. So people know how like common envelope efficiency cannot monotonically explain all the binary. People know that, but still, whenever they're trying to constrain common envelope, they just want to get out one number. So what means is like, in the previous inference, I give you a common envelope, and that's what people think of. Like, okay, give me a number, 0.5, good, and give me the uncertainty. But people have the hunch of like, this actually should depend on mass somehow, right? Because maybe neutron star is more subject to common envelope process because they have smaller core, whereas black hole has bigger core, so they are less subject to the envelope and stuff like that. So people have that hunch, but they always assume single. So actually, I have that plot of showing common envelope efficiency. If you infer on the catalog, it actually goes from I think it goes from high alpha to low alpha. So for high mass event, you actually don't need such high common envelope efficiency to produce them, and for low mass event, you actually need a high common envelope efficiency. So you show a dependency of alpha given m. So yeah, like there are quite a lot of things that we're gonna make some splash with you by having this plot. But yes, alpha is probably the most interesting.